So as an exercise, let A and B be sets. Prove that A is a subset of B if and only if the union of A and B is the superset B, and A is a subset of B if and only if the intersection of A and B is the subset A. So new definition: an ordered pair AB is the set whose elements are the set which contains the single element A, and a set which contains a single element is called a singleton, and the set which contains A and B. That is the ordered pair AB is the set which contains the singleton A and the set AB. This definition is known as the Kuratowski definition, which gives an ordered pair in the language of sets where there is where we are able to distinguish between the first element A and the second element B. And this definition allows us to very precisely prove that an ordered pair AB is equal to an ordered pair CD if and only if A is equal to C and B is equal to D. So proof: we'll do the easy part first. Let A equal C and B equal D. Then the singleton containing A is equal to the singleton containing C, and the set containing A and B is equal to the set where we replace A with C and replace B with D. And so the set containing the singleton A and the set AB is equal to the set which contains the singleton C and the set CD, and hence the ordered pair AB is equal to the ordered pair CD. So conversely, let the ordered pair AB be equal to the ordered pair CD. Then the set containing the singleton A and the set containing the elements A and B is equal to the set containing the singleton C and the set containing the elements C and D. So we consider two cases. Either A is equal to B or A is not equal to B. So first, suppose that A is equal to B. Then the set containing the elements A and B is the singleton containing A. And so the ordered pair AB is the set containing the singleton A. And thus the set containing the singleton A is equal to the set containing the singleton C and the set containing the elements C and D. Now, since the set on the left contains a singleton, the set on the right must also contain a singleton. And so the singleton containing A must be the singleton containing C, and the singleton containing A must be the set with the elements C and D. And thus C is equal to A and D is equal to A. That is, A is equal to B, which is equal to C, which is equal to D. And in particular, it is true that A is equal to C and B is equal to D. So now suppose that A is not equal to B. Then we are back in this case where the set containing the singleton A and the set containing the elements AB is equal to the set containing the singleton C and the set containing the elements C and D. And so the singleton, the set containing only the element A, is an element in the set containing the singleton C and the set CD, and thus either the singleton A is equal to the singleton C, or the singleton A is equal to the set containing the elements C and D. We don't know the relationship between C and D yet in this case. So in either case, the element C is in the singleton containing A, and so C is equal to A. Similarly, the set containing the elements A and B is an element in the set containing the singleton C and the set containing the elements C and D. So either the set containing the elements A and B is the singleton containing A, or the set containing A and B is equal to the set containing the elements C and D. Now, since A and B are distinct, A is not equal to B, this set is not equal to the singleton. And so we have that A, the elements AB is equal to the elements CD, where C is equal to A, and so this is the set containing the elements A and D, and so B equals D. That is, A is equal to C and B is equal to D. And therefore, the ordered pair AB is equal to the ordered pair CD if and only if A is equal to C and B is equal to D. Okay, so new definition. Let A and B be sets. The Cartesian product of A and B, which is denoted A cross B, is the set of all ordered pairs AB, where the first element in the pair comes from the set on the left of the cross, and the second element in the ordered pair comes from the set on the right of the cross. That is, in compact notation, A cross B is the set of all ordered pairs AB, where A is in the set A and B is an element in the set B. So let's look at an example. Let A be the singleton containing 1, and B be the set containing the numbers 2 and 3. Then A cross B is the set containing the ordered pairs 1, 2 and 1, 3. The Cartesian product B cross A is a set containing the ordered pairs 2, 1 and 3, 1. So notice that if A is not equal to B, then in general, A cross B is not equal to B cross A. B cross A. One of the exceptions is the Cartesian product of the empty set with a set A, which is equal to the Cartesian product of the set A with the empty set, which is the empty set, because if we're taking a Cartesian product with the empty set does not have any elements to contribute to an ordered pair. Okay, so new definition. Again, let A and B be sets. A relation R between A and B is a subset of A cross B. That's any subset, including the empty set. So if the ordered pair AB is in the relation R, we say that A is related by the relation R to the element B, and we write A is related to B. And if A and B are the same set, R is a relation on the set A. So let's look at an example. The familiar less than equal relation is a relation on the set of integers for every pair of integers A, B. Either A is less than or equal to B, or B is less than or equal to A. Or both in the case that A and B are the same element. Okay, so new definition. An equivalence relation which we'll call R on a set S is a relation satisfying the following properties. One, for every element X in the set S, X is related to itself. For every pair of elements X and Y in the set S, if X is related to Y, then Y is related to X. And for every three elements X, Y, and Z in the set X, if X is related to Y and Y is related to Z, then X is related to Z. The first property is known as the reflexive property. That is, the relation is reflexive. The second property is known as the symmetric property. The relation R is in an equivalence relation, the relation R is symmetric. And the third property is known as the transitive property. So the symbol tilde, or the symbol for similarity, is often used to denote an equivalence relation. So let's look at an example. Let P be the set of all polynomials in the indeterminate X with integer coefficients let tilde be a relation on this set defined by the polynomial f is related to the polynomial g if and only if the derivative of f is equal to the derivative of g. Show that this relation is an equivalence relation. Okay, so new definition. Let tilde be an equivalence relation on a set S the equivalence class of an element A in the set S is the set, which we denote this way, and this is the set of all the elements X in the set S such that X is related to the element A. And the element A is called a representative of the equivalence class. Okay, so let's end here for now. Next time we will look at how equivalence classes partition a given set, and then we'll continue with a special type of relation called a function. So I hope you have enjoyed the third lecture. Thanks for watching.